Hey, this is Dr. Stotts. I'm going to do this video walking you through significant figure rules. It can be kind of confusing if you're not there to do some practice and whatnot. But it's pretty straightforward, and the rules are really simple. It's new information, so that's really the most difficult part about it. So we're going to just take it one step at a time, and I'm going to talk about each rule, and you should be good to go. First off, just to introduce sig figs, and sig figs is short for significant figures. In chemistry, any number that we work with, we pretty much assume that it's some sort of measurement. So significant figures, if I can say it, it's all about measurement. And when we work with measured numbers, there's a certain level of precision that we talk about and how precise our measurements are. And when we measure things in the lab, our precision is always limited by the instrument that we're using. For example, you've seen us, you've used these types of balances and scales in the lab. If you notice on the picture on the left, this balance, let me get a marker going here so I can write a little bit. All right, if you notice the image on the left, this scale, this balance only measures in to the 10th of a gram, so it's going to be 0.6 or whatever that might be. But it's only measuring out to the 10th of a gram. So it's only precise to the 10th of a gram. Whereas a balance like this, if you could blow that up there, you would see that it's out to the 1,000th of a gram. So in this case, it's pretty obvious which one of these instruments is going to give us the most information. It's going to be more precise. It's going to be the balance over here that's got the measurement out to the thousandths place. So we're limited in precision by the instrument that we use. And another example of that, and you'll see how this plays into the sig figs here shortly. If we've got two graduated cylinders, you've got this cylinder here on the left. It's a larger one, and if you were to look at the increments that it's using to measure, each one of these increments is 50, but if you zeroed in there and you really analyze, you would see that each one of those dashes represents 10 milliliters. Okay, whereas a smaller graduated cylinder, if you look at this one, this is the entire graduated cylinder holds 10 milliliters. So each one of these increments is 1 milliliter, but then there's even smaller units in there that measures to 2/10ths of a milliliter. So obviously between these two instruments, which one is going to be more precise? It's going to be the smaller graduated cylinder because it's got a more precise digit there. Okay, so these decimal points and these numbers, all of these digits play into significant figures. And so when we look at sig figs, there's a certain number of rules that we use to determine how many numbers or how many significant figures a number has. So rule number one is that any non-zero digits a number has, they are considered significant. So if I take a measurement and it's 268.7, now look at and it could be milliliters or whatever unit. When I look at that number, I see all of those numbers there are non-zeros. So in this case, I would say all of those numbers are what I call significant. And when we talk about significant, it's not that numbers aren't important, it's just that in terms of measurement, each one of these holds a certain level of significance in terms of precision in the measurement. So in this case, I've got 4 non-zero numbers, so I would say that this number has 4 sig figs. Okay. Another number, let's throw in 300. Let's go there, 378. All right. Again, 3 non-zero digits, so this number has 3 sig figs. That's the easiest rule to start with. So 3 sig figs for this number. All non-zero digits are considered significant. Okay, and you're going to find that really all of these rules focus on zeros and whether or not we would consider a zero significant in a number. All right, second rule. Any sandwiched zeros are significant. I call this rule the guilty by association rule. So if I look at a number like this, 209, well, going back to rule number 1, we would say that this 2 and this 9 are both considered significant. Okay? Now this 0 that's in the middle here is what we would call, it's sandwiched. It's stuck right in the middle of 2 significant figures. So it's guilty by association. So we say that it also is significant. So that number would have 3 sig figs. Okay. Well, what if I had more than one 0 in there? The same rule applies. This 2 is significant according to rule number 1. This 9 is significant. And we've got 2 zeros in there that are sandwiched between 2 significant figures. So in this case, we would say that all of those are significant. So 4 sig figs. And that pattern continues. It doesn't matter how many zeros you have that are sandwiched between 2 significant figures. If there's a non-zero, so it's significant. There's a non-zero, it's significant. And all of these zeros are squeezed in between those 2. So they're guilty by association. So this number has 3, 6, 9, 10 significant figures. Okay, so rule 1, let me back up. All non-zero digits we say are significant. Rule number 2, if a 0 is sandwiched in between 2 significant figures, it also becomes significant. And that takes us to rule number 3. Here's where we get a kind of a tricky rule. Trailing zeros are not significant. They're simply viewed as placeholders. And then we'll talk about scientific notation. So if I have a number like this, 640,000. 640,000. All right, so when I say trailing zeros, I'm talking about zeros that come at the end of a number, a non-decimal number, that is. So these zeros come at the end of 640,000, obviously. So we would say that those are not significant, and here's why. Technically in science, if we can write numbers in scientific notation, that's always a benefit. And if you remember scientific notation, that's where we move our decimal place until we get it in between 2 numbers that are between 1 and 10. So there's 6.4. So if I do that, and this becomes 6.4 times 10 to the 1, 2, 3, 4, 5. So remember, that's how scientific notation works. I'm pretty sure that you guys talked about that in pre-algebra or even middle school. So if I move my decimal, I really get rid of all those zeros. I can write that number in a way where I don't have all of those trailing zeros. So in this case, how many significant figures did that number have before? Well, the 6 and the 4. If I write it in scientific notation, how many significant figures does it have? The 6 and the 4. And by the way, that's how we read sig figs in scientific notation. You analyze this first leading number there. That's called the coefficient. So if you had 2.6 times 10 to the negative 4th, that would be 2 sig figs there. Okay, so let's look at a few more of these trailing zeros. If I have the number 10, oh, there's a trailing 0. That's a 0 that's at the end of a number, and it's just considered a placeholder. That doesn't mean that it doesn't have value, but we just don't consider it significant in terms of measurement, because I technically could write that as 1 times 10 to the 1. and there is one significant figure right there. So 2400. These zeros are not significant, so I would say that there's 2 sig figs there. 1,600,000 or 1,064,000. All right. So really, it's all about the zeros, right? So we know that this 1 is significant because it's a non-zero. This 6 is significant. It's a non-zero. Same with the 4. But now this 0 here, we would say, according to rule number 2, it's sandwiched, so there's 4 sig figs there. But these zeros here, they're not significant. So this number would have 4 sig figs. And if we were to rewrite that in scientific notation, it would be 1.064 times 10 to the 1, 2, 3, 4, 5, 6, 10 to the 6th. And there is your 1, 2, 3, 4 sig figs. So trailing zeros are not significant if they're at the end of the whole number. Okay. Well, what happens if those trailing zeros come at the end of a decimal? Well, in that case, zeros to the right of the decimal point are only significant if they are at the end of the number or if they're sandwiched. So let's look at several cases here. If I have 0.00064, okay, and obviously the zeros are the ones that are in question. I know the 6 and the 4 are significant, but if I look at these zeros here, those zeros, although they are to the right of the decimal point, they are not at the end of the number. They're not out here, so they're not considered significant. And it kind of goes back to the scientific notation rule. I could rewrite this decimal in scientific notation as 6.4 times 10 to the negative 1, 2, 3, 4. Remember, if we move the decimal point to the right, it's a negative exponent. So if I write that number in scientific notation, how many sig figs do I have there? 2. So zeros in front of the decimal portion right there, I mean, they're after the decimal point, but they're between the decimal and that first significant figure. They are not significant. Okay, so if I have 0.03200, obviously the 3 and the 2 are significant because they're non-zeros. Now, these zeros at the end here, this is not like rule number 3, where we said that all trailing zeros at the end of the whole number are not significant. These numbers are to the right of the decimal, and they are at the end. So that means they are significant. And the reason for that is, let's think back to when I showed you the balance that measured in to the 10th of a gram. So let's say that I was measuring something out and it came out to be 0.100. Now, because I was using a balance that was able to give me a very precise measurement, this measurement that I'm looking at, 0.100, that was exact. It was 0.100. It wasn't 0.101. It wasn't 0.009 as a measurement. It was exactly 0.100. So in this case, those zeros indicate a very precise and exact measurement. So we've got to consider them as significant. So again, zeros to the right of the decimal and at the end of the number are significant. So in this case over here, 0.03200, there's 4 sig figs there. The 3, the 2, the 0, and the 0. So a couple more on that just to make sure we're squared away. 602.00403. It's a crazy number. So how many sig figs? The 6, yes, because of rule number 1. 2, of course, and the 4 and the 3. So those are all non-zero numbers. Well, what about this 0 here? Well, this 0 is sandwiched between the 6 and the 2, so then that means it's significant. These two zeros are sandwiched between the 2 and the 4, so that makes them significant. And this 0 is sandwiched between the 4 and the 3, which means it is significant. So in this case, every single number is a sig fig. So there's 3, 4, 5, 6, 7, 8. I think 3, 4, 5, yeah. So 8 sig figs there. All right. What about 2.0600? Okay, of course, the 2 and the 6. This first 0 is sandwiched in between the 2 and the 6, so it's guilty by association. And these last two zeros here are to the right of the decimal and at the end. So they also are considered significant. So we've got 5 sig figs. All right, so we've got a couple special rules here. Special rule is if a number ends in a decimal point, it indicates that it is an exact measurement, and thus all numbers are considered significant. So going back to that image of the balance again, the electric balance. If I'm measuring something out and I get, it comes out to 150. Well, by the normal rules that we just talked about, there's only 2 sig figs in that number, the 1 and the 5, and that 0 is a placeholder. Well, let's say that we were measuring something and it came out to be exactly 150, and we knew that based off of the instrument of measure, and so that 150 is an exact number. It's not 149, it's not 151. We have measured it out to be exactly 150. And if we want to indicate that, we just put a decimal point there at the end. So if we see a decimal point in chemistry, and obviously, we don't use the decimal point at the end of a number there if we don't need to, we just leave it off. But if we see a random decimal point at the end of a number, that means that is an exact measurement, in which case all of those numbers become significant. So 3 sig figs in this case. So it doesn't matter how many numbers we have, if it ends in a decimal, all of the numbers are considered significant. So in this case, 7 sig figs, because the decimal point indicates an exact measurement. All right, so before I move on to the next slide, I'm going to insert a slide here and talk a little bit about rounding sig figs. Rounding sig figs. So if I have a number, let's say we've got 206.09. Let me throw in some other non-zero numbers here. 246.17. Okay. If we were to be asked to round this number to a number that only has 2 significant figures, here's what we would do. Anytime we have to round a number with sig figs, let's say in this case we're going to round to 2 sig figs. What you have to do is you always have to start with the numbers that hold the most value in the number, or the places, the digits that hold the most value. So in this case, the 2 is in hundreds place, and the 4 is in the tens place. So those 2 hold the most value. So those would be the 2 significant figures that I would round to. So I come over here to this 4, I look to the right of it, and I just use normal rounding rules. That 6 is higher than 5, so that 4 is then going to go up, and then that 6 becomes a 0, and everything else drops off. So 250 has 2 significant figures, So 246.17 rounded to 2 sig figs is 250. Okay, if I wanted to round that number to 3 sig figs, well, likewise, I would come over 3 digits. There's my 3 most valuable digits in terms of value: hundreds place, tens place, and ones place. And then I look to the right. That's a 1. So that means that 6 is going to stay the same, 246, and then the decimal drops off. What if I wanted to round to 1 significant figure? Well, I just look at that first place value, the 2, look to the right, that's a 4, so everything else drops off. That 2 stays a 2. Okay, let's take a look at some decimals. If I have 0.00637, round to 2 significant figures. Well, I have to come over to these 2 most valuable places here in terms of value, the 6 and the 3. So there's my 2 sig figs. That 3, I look to the right, that's a 7. So that means that 3 goes up to a 4. So there's my 2 significant figures in rounding. If I was going to round that to 1 significant figure, 0.006, because I would look at that first value. That 3 tells me that 6 is going to stay the same. So that would be rounded to 1 sig fig. Okay. So now let's get into the last 2 rules. And I know this has been, we got like 20 minutes already, so hopefully you've taken a break and paused if you needed to. Now that we know how to look at a number and determine the number of significant figures, now we've got to roll that into when we actually do calculations. And I always get asked the question of, how many digits should we round our answer to? Should we go to 1 decimal place or 2? Well, these rules that I'm getting ready to discuss, they actually answer that question for you. Now, I have to preface this by saying that when you get into college chemistry, there's going to be some professors that are very, very strict on sig fig rules. And once you talk about sig figs at the beginning of the year, they're just going to expect you to use sig fig rules in every calculation for the rest of the year. And there's going to be other professors that are going to say, okay, yeah, we're going to go over them, but just round your answer to 2 decimal places in the lab. And then they don't really abide by the rules. So, I can't predict which type of professor that you're going to get, so we're going to go over the rules and make sure that you know them. So, the rule for adding and subtracting. Now, as we read the rule, it might not make sense until we actually look at an example. So, the rule is, when adding or subtracting measurements, I should say, the answer should have the same number of decimal points as the number with the least number of decimal points in the problem. And what that means is that we can't have an answer at the end that's more precise than the least precise number in the calculation. So let's take 2.45 plus 3.062. All right, so the very first thing we do is we simply do the math like we normally would. So you can break out your calculator if you don't want to fool with the decimals at this point. So if I do that math, I get 5.512 for my complete answer. Okay, so now, assuming that these are measurements, I've got to use sig fig rules. So according to the sig fig rule for addition and subtraction, my answer down here can only have the same number of decimal points as the fewest number in my problem. So when I look at 2.45, I've got 2 decimal points there. Look at 3.06, I've got 3 decimal points there. So that means that 2.45 is the least precise number in that calculation. So that means my answer cannot be more precise than that one. So my answer also has to have 2 decimal places. So I just use my rounding rules and look to the right, and that becomes 5.51. Okay. So pretty straightforward rule. It's just new. It's not difficult. Let's say we've got 10.03 plus 3.5. Well, I simply do the math. 13.53, and I get my full answer. Then I look back and analyze the number of decimal places. I have 2 decimal places in that number, 1 in that number, so that means my answer can only have 1. So 13. I look to the right, round, so 13.5 is my answer. All right. Sometimes you encounter this scenario where, so 3.5 plus 6. Well, I do the math, get my answer, 9.5, and then I look at the number of decimal places. I've got 1 decimal place here, but I don't have any decimal places there. I've got a whole number. So if I don't have any decimal places, the number of decimal places is 0, and 0 is fewer than 1, so that means I have to round my answer to a whole number. Okay. So the next rule is for multiplication and division. And if you notice back on the addition and subtraction rule, it was all about the number of decimal points in the problem. Whereas in multiplication and division, it's all about the number of significant figures. So when multiplying and dividing, the answer should have the same number of significant figures as the number with the fewest significant figures in the problem. So 2.45 times 1.003. Okay, so I do the math just like I normally would. So 2.45, I'm plugging this on my calculator, times 1.003. And I get a full complete answer of 2.45735. Okay, so if we were doing this in lab, somebody would ask me, well, how many decimal places should I round our answer to? Well, now you know this rule for multiplication and division. It says that our answer should have the same number of sig figs as the number with the fewest in the problem. So when I go back up and look at the numbers in my problem, 2.45, each one of those numbers are significant, so that number has 3 sig figs. If I look over here, 1.003, the 1 is significant, the 3 is significant, these zeros are sandwiched in between, so that means they all are significant, so 4. And obviously 3 is fewer than 4, so I've got to make sure that my answer down here has 3 sig figs. So I use my rounding rules. There's 1 sig fig, 2 sig figs, 3 sig figs, so I'm going to round it to that 5, so 2.4, and that 5, I look to the right, that 7 is higher than 5, so 2.46. That's my answer there. Okay, let's do a few more. What if we have a fractional problem like 6.98 divided by 1.0? I don't know if that'll be 1.0 because it's going to be the same thing. 3.0. So we do the math. That's division. 6.98 divided by 3.0 equals, I get 2.326666 repeated. So according to the rule, I look at the number of sig figs of each of these numbers. There's 3 sig figs here. 1, 2, 3. Down here there's 2. That 3 is significant, and that 0 is significant because it's to the right of the decimal and at the end of the number. So 2 sig figs there. So in this case, 2 is obviously smaller than 3, so it's the fewer number, so my answer has to be rounded to 2 sig figs. So 2 and the 3, so my answer is 2.3. Or I'm sorry, I wrote a 2, but it should be 2.3. Okay, so if we have another example, let's say we have some mixed calculations here, and we've got 6.07 minus 2.4 divided by 1.50. Alright, so at the very top here, order of operations says that we've got to do the subtraction on top of this fraction first, and that's a subtraction problem. So if I do that math, 6.07 minus 2.4, on top I get 3.67 for a total answer. But that's a subtraction problem, so I've got to make sure I follow the significant figure rules for subtraction. My answer has to have the same number of decimal points as the fewest number in the problem. So if I look at my decimal points, 0, 7, so there's 2 decimal points there, and 0.4, 1 decimal point there. So I have to round my answer over here to 1 decimal point. So obviously that's going to be 3.7. I'm going to go ahead and change that to 3.7. So now I've got 3.7 divided by 1.50. So this is a division problem. So I divide 3.57 divided by 1.5, and that equals 2.38. Now here again, this is a division problem, so I have to look at the rules for sig figs for multiplication and division problems, which says the answer should have the same number of sig figs as the number with the fewest in the problem. So when I look at the problem, 3.7, there's 2 sig figs. 1.50, there's 3 sig figs. So that means my answer has to be rounded to 2 significant figures. So the 2 is significant, the 3 is, so I look to the right, and that 8 tells me that the 3 has to bump up to a 4. So my technical answer, including all sig fig rules, is 2.4. Okay, so I'm going to stop there. That's about a 30-minute video. I know it's a lot. Hope you took some breaks in between, and I'm going to let you use these rules and let it process, and let you go back and do some practice on the sig fig practice that is loaded in OneNote. And if you have any questions there, you can let me know, and we will touch base and make sure that you get squared away and have all of your questions answered. All right. Have a good one. I'll see you again.